All right, hey, welcome back. In this video, we're going to talk about using integral tables to integrate difficult integrals. At this point, honestly, you've seen all of the main techniques we have for identifying integrals algebraically. In the next section, you'll see how we have a numerical way of attacking integrals that we can't actually algebraically evaluate. But in this video specifically, what I want to talk about is how to use integral tables. These are tables of really difficult, complicated integrals that you can use pre-formed formulas for to help you solve the integrals or reduce the integral you're working with to be a solvable integral. On the face, it might seem easy or cheating to use a table, but you're going to see there's actually a lot of work that we can do to integrals to make them of the form that makes an integral table useful. In this case right here, we have the integral of the square root of 5x squared minus 2 over x squared. And what we want to do is to integrate this with a form that we can find in our tables here. So let's bring up our table of integrals that we have. There are many different forms of this, but generally all of the integrals that you'll see are of the same sense, no matter what your textbook. But in the OpenStax textbook, we have this list right here. We start off with these basic integrals and go through some of them that we've already seen. If we scroll down, what we're looking for in this case is an integral of this form, specifically a fraction. We have a square root in the top where we are subtracting a variable part squared and a constant right here. So if we go down, we now have gotten to the point where we have a variable part minus a constant, and then right here, number 80. So number 80, which is the square root of u squared minus a squared over u squared, that's nearly the same as this right here, and we can use this formula to attack this. The main job that we're going to have to use this formula is we need to rewrite this integral in that exact form. We're going to use a u substitution to bring this, to make this into a simple integral or a more simple integral of exactly that form, the integral of u squared minus a squared over u squared. So this information gives us a lot, but does not solve this for us. What we need to do now is take this integral, importantly the expression on the inside, and rewrite it so it's exactly this using a u substitution. When making this u substitution, what I'm going to realize is that the stuff inside the square root is going to be more work to deal with. So what I'm going to do here is I want this u squared part right here inside the radical to be equal to this 5x squared. So this is my thinking right here. I want u squared to be the same as 5x squared. This helps me think about what I want directly for my u substitution. Well, if I want u squared to be this, then I'm just going to take the square root of both sides to get that u equals, and I'll square root both of these individually, the square root of 5 and then times x. Then I'm going to differentiate both sides to do this differential swap. So I get du equals the square root of 5 dx. And then as I always do, I'm going to divide over this constant to get 1 over square root of 5 du equals dx. Important to note here, I'm not going to mess with this 2 at all. I'm just going to say, and I'll write it here real fast just so I don't forget, is that 2 equals the a squared. That's going to be important when I come back to this. If I had an a in my formula, which I actually don't in this case, but if I had an a, then a would be the square root of 2. But let's actually move forward here. What do we got here? I made this substitution of u equals the square root of 5x. And so now I have the integral. With that substitution, I know that this 5x squared part becomes u squared. So that's really important. That's what I wanted. So I got u squared right here. Minus 2 is my a squared. And then when I do my swap with my differentials, dx is this 1 over square root of 5 du. So I'll make that swap right now, and I'll put that constant out here out front. And now I need to replace the x squared. I don't have what x squared is equal to, but it's simply from right here. I'll just divide 5 from both sides to get that 1/5 u squared is the same thing as x squared. So with this substitution, I'll replace x squared with 1/5 u squared. And there I've actually done most of the work. What I'm going to do, I have this 1/5. I'm dividing by this 1/5, so I'm just going to flip this and multiply. Out front here, then I'll get a 5 over the square root of 5. And then I have the integral that I am looking for here, u squared minus 2 over u squared du. So then at this point, I actually know this integral is this right here. And I guess it could be useful maybe to write that down directly right here, but that's not what I'm going to do. I'm actually going to do it and plug my information, my x information and my a squared information as I do that right there. So again, I'm using that formula here, but I know that u in this case is the square root of 5x. I know u squared is 5x squared, and I also know that my a squared is 2. So putting that all together, also 5 divided by the square root of 5, that is just the square root of 5, by the way, so I'll have that constant out front. And then I have the rest of this jazz. So I have the square root of u squared minus a squared. So I have this, so this is negative the square root of u squared is 5x squared minus a squared, which is 2. All over u. U is the square root of 5x plus the natural log of u. That was u right there. So the square root of 5x plus the square root of u squared, which is 5x squared minus a squared, which was 2 plus c. All right, and that's meant as an introduction to this concept. Again, the work that you're doing is taking something of the form here, finding something in the table that looks similar, and again, these u's are representing just generally variable parts. Any constant times a variable is not that complicated to deal with, as was this 5 here next to this 5x squared. It just gives you out these extra little factors that come out. But the job is to make that look exactly like this form with your substitution. Make sure you're keeping very careful track of these things like u squared, u, a squared, and you're often going to need like a also. So keep track of those so then you can just plug and play those right into the formula that you're given. We're now going to look at a bit more complicated example. It'll take us a bit more, and we're going to use multiple different tables, our integrals from our tables to evaluate. All right, in our second example, this is a fun one. We're going to use these 3 tables right here. And I just want to say this about these 3 formulas and many of the formulas that you'll see on the integration tables is the fact that these, so in this case right here, I'm looking for u raised to the n power times the cosine of u. If you look at this, these are called reduction formulas, these first 2, to where you start with the integral and you're still going to have an integral. The idea is you've reduced the integral a bit. My hope is that you notice the form of this right here. In almost all of the cases, these reduction formulas are using integration by parts. So what that means is we actually could use integration by parts in a few different steps when I apply these right here. Specifically, when I use both of these, I could have used integration by parts instead. But with these, when I'm using these, I actually don't have to go through the process of integration by parts. It's been formulaically done for me in these cases right here. This would actually be another integration by parts, though we wouldn't call this a reduction formula. Let's get to the work. So in this case right here, I need to make this look like in one of these right here. Specifically, I'm looking to make it this. As before, and I said it with a square root, but generally speaking, when I do my u substitution, I want to make it for stuff that's an inner function, because that's the more difficult stuff to deal with. Like in this case, I could just let u equal t, but what I'm going to do is let u equal the 3t on the inside here. And hopefully as I work through this, you'll see the reason for that. So this is going to be my substitution, though I want to make this statement right now, and I'll just do it as an arrow up here. If I divided 3 from both sides, I would also get that t equals u divided by 3. That will be useful for me when I move forward. So if I have this, what I get is that du equals 3 dt. And then, given that, I'll divide over the 3 to get a 1/3 du equals dt. So then making the substitution gives me the following. So I have t cubed. This is the reason I wrote this up here. So t is u divided by 3. So this becomes u divided by 3 cubed. And then I have the cosine of just u right here, because u is the 3t. And then I get a 1/3. I'll put the 1/3 out here. And I get the swap for dt to du. I'm really close to getting it to this form right here. I just have to deal with this. What I'm going to do is apply the exponent of 3 to both of these. I get u cubed over 3 cubed, which is 27. I'm going to pull out the fact of the division of 27 there, the 1/27th, multiply it by this to give me 1/81st times the integral of u cubed cosine of u du. So then now applying number 40 right here tells me that this, in this case, my n is 3 and everything else is the same. So just as I have the n's through here, those are going to be the values that I'm told I have. So I get 1/81st times, make sure I put this all being times by that 1/81st right there. So u to the n, that was still u to the 3rd, times the sine of u, okay, now minus n times the integral, so n is 3 in this case. The integral, now I have u to the n minus 1, which means now I have u squared, excuse me, times the sine of u du, and then plus c. All right, so applying the formula for number 40 got me to this statement right here. Though as you see in it, I'm still left with this integral. What I'm going to do now, and this is where visually it kind of gets intense, but I'm now going to attack this integral right here with this. The beauty of this is I don't need to do any more substitutions because I've all just normalized this just to have u's and be all kind of in this nice real formulaic way. But what I need to do is to this part right here, let's get a color here. So this part right here, I'm going to use this formula right there. And so let's see what that ends up looking like when I do it out here. So I got the 1/81st, that's all the same. This is u cubed sine of u minus 3. Now this thing, using that formula, this becomes negative u to the n. So let's get some more, let's use parentheses this time right here. So negative 3 times negative u to the n, so that'd be negative u squared in this case, times the cosine of u. By the way, that should not be x. That should be a u. Okay. U plus n. N in this case was a 2 times the integral. And now I have n minus 1. 2 minus 1 is 1. So I have u to the 1 power cosine of u du plus k. And important to say in this case is that I'm going to have this running constant that I'm going here. I'm going to change it every time just to be really accurate, but it doesn't really matter. It's an arbitrary constant either way. It's really this c plus this new c value. But anyways, I still have this integration constant. Finally, as was the case with this last time, when I do that, this reduction formula gives me an integral to deal with, which is this right here. So I'm now going to attack this and with this formula right here. And hopefully it's maybe obvious. I'm trying to make this clear, but it does get pretty convoluted. The one thing that's kind of important that you might mistake is how you apply these factors, these constant factors on the outside. Is this 1/81 is multiplied to everything. This negative 3 that's right here is multiplied to all of this stuff that was the result of this integral. And now this 2 right here is going to be multiplied by the 2 factors that I'm going to get when I rewrite this. But let's see if I can do this without screwing it up. So here we go. I have 1/81 times the quantity u cubed sine of u minus 3 times this negative u squared cosine of u plus 2 times, I guess I'll just use parentheses again here. Okay, now u cosine u du is this right here, so that becomes the cosine of u plus u sine of u plus my c but I'm just going to keep that there. And actually, I'm going to move this constant all the way to the outside. Let's see, I got this, I got that, so double parentheses, and I got this bracket. And then I'm being a little bit lazy with my notation here. Some instructors are really anal about this, but the game is, you're going to do several integrals that are each doing an arbitrary constant. I know I said this before. The idea is just at the end, make sure at the very end, you're adding this plus c for this constant. I mean, you could say big C is a combination of -3 times k and 1/80th times c or whatever. It doesn't matter. I'm probably talking about it way too much. But again, that step was taking this integral and rewriting it in that form right there. That's really the main integration work. All I need to do now is make sure I answer back in terms of t. And again, just to say it for these, and these more complicated ones, if you use multiple different integral tables, is the fact that, well, I only really got to do the substitution once, and then I kind of have it, what I call it normalized. Like it doesn't have strange variable parts anywhere. It's all just u and pretty formulaic. But at the very end now, what I need to do is take this expression, rewrite u in terms of t, and that simply will go like this. I got this 1/81st, and then u, is 3t, so this becomes 3t cubed sine of 3t minus 3 times negative 3t squared cosine of 3t plus 2 times the quantity cosine of 3t plus 3t sine of 3t. Close those parentheses, close those parentheses, close that bracket, plus c. At this point in your head might come the conversation of like, shouldn't we now distribute? Should we expand this? Should this be 9t squared? This should be 27t cubed. And then distribute this -3 and the 2 through the parentheses. And I would say, for sure, like if you had a reason for doing that, like if you had to solve an equation afterwards, though an equation involving all this would be pretty freaking gnarly. But the point being, to me, at this case, is you found the integral. Like here, you found it in terms of t. I don't think you need to multiply it out unless you have a reason to. And again, to show you this is a really gnarly integral. And you think unless still took a lot of steps. But yeah, think about the fact that what these did for us. Again, these are prescribed, all three of these actually are a prescribed integration by parts that are injected into this formula. You could have done the integration by parts each time, but using these formulas allow us to not have to go through those steps, though we have to get it into this form. That's always the case when using tables, is that first substitution, manipulation, algebraic tricks that you're going to do really unlock everything else. And then the game is don't get lost in all of the business as you're actually applying these, because obviously with all the different notation and looking at these formulas, that can happen too. Let's look at one more example where you got to do some tricky manipulation to get it in the form that we want. All right, so the first example just basically introduced you to the idea of how to do the u substitutions, right? To get them into these general forms. The second example was like, well, by the way, we could use multiple, and sometimes we'll have to use multiple of these formulas. And we're going to have some reduction formulas, but we're going to have some integrals that we still have to tack all the way down. This is of a very different method. This is simply going back to that idea of the u substitution and needing to do some algebraic tricks to get it in the form that you have. What my statement here is I'm going to use this formula right here of 1 over the square root of a squared plus u squared, which, by the way, I could write this as u squared plus a squared, but for some reason, generally, we like to write the constant term first. Equals this right here, the natural log, the absolute value of u plus the square root of a squared plus u squared, absolute value, and then plus c. The game is we want to get it of this form right here. And for me, I would look at this and be like, well, awkwardly, this has one term of u squared and not this x term right here, but we actually can get this to look like that using our friend of completing the square for this right here. And I'll talk about this. And again, this is one of these side algebraic tricks. Let's use yellow here. So what I'm going to have is, so x squared minus 4x plus 10. What I'm going to do is I'm going to split off this 10, and I want to complete the square with these two terms right here. So what I'm going to do in this case, whenever you complete the square, what you need to do is take half of this and then you square that and add it on, right? So negative 4 divided by 2 is negative 2. Negative 2 squared is positive 4. So I'm just going to add a positive 4 on there. That completes the square with these terms right here. That's a perfect square trinomial. Though, hopefully you're thinking, Mike, you're not allowed just to add 4 to one side to an expression. It doesn't stay the same. What I need to do if I add 4 here is subtract 4. I want to make one statement here also, and it's exactly the same way of thinking. Instead of doing this move of adding and subtracting 4, what I could have done instead is I could have broke this 10 up into a plus 4 and a plus 6. It wouldn't have actually mattered, but this is the general technique that we use. So you don't need to think about, like if you have an interesting or negative constant there, you don't need to think about taking away a positive from a negative and the effect of that. But I digress. Here we go. So in this case right here, I've completed the square. X squared minus 4x plus 4 now factors into x minus 2 squared. That was the reason for creating these terms right here. And you may notice, and hopefully you've had experience with this in previous algebra, this move takes an expression, a quadratic expression, and instead of having multiple terms with your x's, you get it down to one term right here. And that's the big issue, the big deal for us that we're going to tackle here. But anyway, so I completed the square there, and then I get this plus 6. So what that means is this right here inside the radical, I can now rewrite this as dx over the square root of, and I'll write the 6 first here just so it's in the form I have over there, 6 plus x minus 2 squared. Actually, I'm compelled a little bit just to make more of a comment about this, and I want to talk about this completing the square and where this 4 came from. So just so you have this, and you can look it up for sure, but what you do is you take this coefficient, the linear coefficient in front of the x, so I take negative 4, I always divide it by 2, so what I'm going to do is divide it by 2 and then square that result. So negative 4 divided by 2 is negative 2, and then I square that to get 4. That's the number that I'm adding here and then subtracting here to balance out that addition. When I go to factor this thing will then always factor to be x plus or minus whatever this number is right here, right? So this factors into x minus 2 squared or x minus 2 times x minus 2. And I knew that because I chose that number for that constant or that term right there. That's really the tough work of this problem. I have my formula here. I have this written way more in this form right here. I do need to make a u substitution. So I'll let u equal x minus 2, and then I get that du equals dx. So it's a straight swap with my differentials. All right, so then what that gives us is we have the integral. I'll do my swap with my differentials here to get du over the square root of 6 plus, now this is u squared. I now have this in the form that I need to apply here. I want to make this statement, so I know that u equals x minus 2. That will make it easy over there. Also, this 6 plays the role of the a squared, so I'm just going to make a note of that for myself. You don't have to say this, but a squared equals 6, just to keep my head on a swivel right here. I don't need to square the 6 or anything, right? Because this a squared, this number is the same as the only place it appears over there. But applying that formula then to this statement gives it that this becomes the natural log of u is just x minus 2 right here, plus the square root of a squared plus u squared. So that would be 6 plus u squared is x minus 2 squared plus c. All right, that's the general strategy for using integral tables. And again, the general thought is you're making u substitutions, or in this case, algebraic manipulations and u substitutions in order to get these into that form right there. There are other tricks that we can use to make this happen. This isn't the full gamut, but gives you an idea of the kind of tricks that we would need to use. And again, once you've gotten those into a form that's exactly the same, when you do this, it's really an attack of the variable parts like this u. These constants, it doesn't need to be a perfect square or anything. It's easy to deal with a constant. If you know this is a squared, you would know that a is the square root of 6, right? But the work is really with these non-constant parts, these variable parts, making it look exactly like of that form there. And then making sure that when you substitute back in, you replace the u and the x. Again, usually when we do u substitutions, right, we would do the integral with the u, and then we would plug in x. The beauty is when we're using tables is that the actual integral part has been done for us. So we don't need to write that. We can go directly from that statement and plug in our u values and our a squareds or our constants as necessary.